I think we are good to go. And let me just get the desktop screen up. And we're good to go. Alright. Hello everyone and welcome back to our C Mathematics series. Today we're going to be continuing on with our AES. This will probably be the last video with AES, at least in this library. We'll probably be looking at just like making it into an application, using it in there. But today we're going to be doing padding of messages, and then we will also be looking at different modes of AES. So we'll start with the simple padding, which is right here. So there are going to be a few different ways to pad. So there's 5 logical ways, or 5 ways that you could think of. There are standards that make sense, but there's one that we will end up using. So you could, for example, when we would need padding is when we don't have a complete block. So, for example, since this is a block cipher, we're going to need complete blocks of 16 bytes. So if we don't have an incomplete block, we're going to want to make it a complete block, but make sure that the way we make into a complete block does not disrupt, or it does not destroy the integrity of the actual message itself. So we're going to, for example, in the example that I gave a while ago, with a message of 49 bytes, we're going to have 3 complete blocks, and then 1 extra byte that we would have to pad with 15 bytes, no matter what it is, to get to a complete block of 16 bytes. So there are 5 standard ways. First one's going to be you're going to pad the bytes with the number of padding bytes. So in this case, we would have our 1 byte from the message, the last byte of the message, plus 15 bytes that represent the number 15. So 15 of 15. You could also have padded with the 0x80, or that's just a simple 1 followed by a bunch of zeros until you get to the end. That could also work. That's called 1 and zeros. You could do a bunch of zeros, you could do null characters, you could do space characters, you could do whatever the fuck you want. We're going to be using the first one, where the number or the padding, we're going to pad with the number of padding bytes. And this is called PKCS5 padding. And the reason why it's used is because it's just simple to know where the message ends. Because if you have a 0x80 as like your indicator for when the message ends, what if your message has 0x80 in there? Well, then you wouldn't know. You could pad with zeros, but what if your message wanted null characters? That could screw things up. You could pad with space characters. Once again, could be a few things, but the standard is to use PKCS5. I'm not entirely sure what this stands for, but what is it? Password based? I don't know. But yeah, so we'll use PKCS5. So every byte that we pad with will simply just be the number of bytes that we pad. So we're going to implement this. It's going to be pretty standard. So let me just pull up my reference just so I know where to look at. And we are going to be starting. We're only going to be doing stuff in AES.C right now. So in AES.C, what we're going to do is we're going to look at our existing AES encrypt function. So for now, we have AES encrypt, which encrypts all the blocks, even if we have an incomplete block. So the incomplete block would be represented right here with the extra stuff that we're encrypting. However, we might not want to do that. well, no, we will want to do this, but to make things a little simpler, we're simply just going to allow all these blocks to be treated as full blocks, but we're still going to pass in the length for each block. So let me just find this real quick. So yeah, we're going to go first to, it's going to be AES encrypt block. So we're going to end up padding. Our existing padding scheme right now is just to add null characters, just zeros, and that was the fourth method here. That was just, we put zeros if there's no text left to encrypt. So what we're going to do instead now is, when we're writing in AES encrypt block, when we are writing in the message to this state array, what we're going to say is state at r at c is equal to another ternary operator, so I is less than n, question mark. So if it is, then we have text to encrypt, so we're going to say in text at I, and otherwise we're going to do block length minus n. So this is just, we're going to be block length minus n is just the number of extra characters that we have to get to a complete block. So that's going to be the number of characters that we pad it with. So use PKCS5 padding. Alright, and then we'll just do I++ at the end. Now, there is a question that arises here. What if we already have complete blocks? So if we already have complete blocks, then we're never going to run into this error here. Or we're never going to run into the condition where I will be less than n, because the number of characters in each complete block is just going to be 16. So we're not going to see this as a reason to add the padding characters. But when we were to decrypt it, how would we be able to differ between whether or not a message was padded? So the goal now is going to be, we're just going to pad every single message no matter what. So even if we have a complete block, we're going to add another complete block just full of padded characters that are all 16. So no matter what, the last character of the decrypted string will be the number of padded characters. So even if it's 16, we will know to remove 16 characters from that encrypted or from that decrypted text to get the message. And so we're chopping off that extra block. So what we're going to do here now is we are going to simplify our encrypt function by a good amount. So we're going to allocate our subkeys, generate the subkey schedule, divide the input into blocks, and then we're going to allocate the output, which is just going to be number of blocks plus 1. So instead of saying out length is going to be number of complete blocks, and then we add to that if we have extra text, we're simply just going to say the out length is equal to number of blocks plus 1, that in parentheses times the block length. So we're always going to have an extra block, so meaning we're always going to pad it. And then what we're going to do is we're going to delete this if-else statement here. So I'm just going to comment it out just so we can compare and contrast. But what this will become now is dereference out is going to be malloc out length times the size of an unsigned character. So we're still doing the same stuff that we were to be doing, except we're just making sure that we always have that extra block. Now, we're going to encrypt the blocks. And it's not just complete blocks, we're just encrypting the blocks. So I'm going to comment that out too. So encrypt blocks. So I'm actually, you know what I'm going to do? I'm going to say number of blocks is equal to, or no, we're good here. So we're going to do our loop. So for int I is equal to 0, I is less than or equal to, make sure it's less than or equal to number of blocks, I plus plus. The reason why we're doing less than or equal to is because, once again, we have that extra block that we did not account for in the counter. I could probably, do I want to, you know what, no, I'm going to make this a little more readable. So we'll do number of blocks is n right shifted by 4, so divided by block length plus 1. So then out length just becomes number of blocks times the block length. And then we're going to do for I goes from 0 to number of blocks, but not inclusive of number of blocks. So just a typical for loop. Now we're going to get the length of the cipher, or of the plain text message that we want to encrypt. So integer length is going to be equal to I is less than number of blocks minus 1, ternary operator here. So if that is true, then we're going to take a block length, because we have a complete block. Otherwise, we're going to say it's extra. Okay, I guess it wants to format it like that. Or no, let me just delete this comment here. There we go. Yeah, so we're going to want to get the length and the length of the message left to encrypt. Length of current plain text block. And then all we're going to want to do now is just encrypt that block. So we're going to say AES encrypt block. We're going to pass in the in-text is going to be the same cursor as before. So in-text plus, in parentheses, I left shifted by 4, because we're moving along multiples of 16. Now the length of the block will just, n here will just be length, because it could be the complete block or it couldn't. But either way, we're going to pass in the length of the block that we're going to encrypt, which will not always just be block length. But you'll see here now that we're kind of combining these, because we did the encrypt extra text and then encrypt block in 2 different steps, where this is going to be the last encrypt, or the last iteration of the loop. So where last time when we encrypted the extra text, that's just going to be the last iteration. So length for the length. Then we're going to have subkeys, same, number of rounds is the same, and then the output will once again just be the same. Dereference out plus, in parentheses, I left shifted by 4. Just like that. And this will do it. This will encrypt everything as expected. And then I do want to note one thing about the encryption, the return value. I'm going to want to just return the out length here. Just because I want to have it in bytes rather than blocks. We're going to be changing a few things with the decrypt function. Okay, so once again, we have pretty much cut all this code out, and we have replaced it with a simple for loop. So I can delete all that, and we see that this looks a lot cleaner. All right, now for decrypt. We're going to go to decrypt, and I'm going to change number of blocks to n, just the length of the cipher. So that parameter is just there. All right, now for decrypt, we're going to do the same stuff. Generate the key schedule, do all that. But this time we're going to do kind of the same calculations as we did in encrypt, where we're going to get integer number of blocks is equal to n right shifted by 4, and then integer extra is equal to n XOR or n bitwise AND with 0x0f, which is just the remainder. Now, I'm only doing this now because we're going to need it in a little bit, but we will now say if extra, then number of blocks plus plus, but this will never arise in our case right now, but we will need this in later on in this video, and we'll see why. All right, so rather than just writing to the output, what we are going to say is we're going to create a temporary string, which will be, so I'm going to once again just comment all this out that we have right now. This is going to be a little more complicated, but we will see how it works. So we get the length. So we're going to allocate a new variable, unsigned character pointer padded out is going to be equal to null, and then padded out is equal to malloc number of blocks times this block length times the size of an unsigned character. So this looks pretty much what we had before. And then we're going to decrypt each block by block. So we're going to do for integer I is equal to 0, I is less than the number of blocks, I plus plus. And then just give me 2 seconds. Alright, and then here we're going to decrypt the block as per usual. AES decrypt block, pass an in cipher plus I left shifted by 4, subkeys as subkeys, NR for number of rounds, and then the output will now be to padded output. So we don't dereference padded out, we're just gonna take the pointer padded out and increment it by I left shifted by 4. So we want to write to the padded output block. It's normal stuff. All right, so that's pretty much what we had before, except we're just changing the location that we write to. All right, then we want to free subkeys, and now we're going to determine the number of padding characters. So unsigned character number of padding is equal to, now if you remember in the padding scheme PKCS5, it's going to be the last character, because we're always going to be adding a block no matter what, or padding to a complete block no matter what, and that may mean adding a full block with 16 bytes. So the last character in the decrypted string will be the number of padded characters. So it's going to be number of padding is equal to padded out at number of blocks times block length minus 1 to get the last character. Alright, and then now we're going to allocate for the output. So we dereference out and set this equal to malloc. And we're going to now allocate only the necessary space. So number of blocks times block length minus padding. So we're going to subtract the number of padding characters because we don't want to allocate for that. This times the size of an unsigned character. And then we're going to copy over the memory. So memcopy, dereference out as the destination. The source is going to be padded out. And then the size of the memory to copy is going to be the size that we allocated for output. So it's going to be number of blocks times blocks length minus padding, or number of padding. And that's all in parentheses times size of an unsigned character. And then we're going to free the padded output. So free padded out. And then the return value will not be number of blocks times the block length. It's going to be number of blocks times the block length minus the number of padding. So only the characters that we sent, or that we encrypted and then decrypted. Or sorry, we only want the characters that were not padded. So yeah, that is going to be our padding scheme. I believe that's everything for the padding, actually. Let me go into main.c and we can try this out. C test, run. Uh-oh. What happened? Oh, yes, I know why. Because we changed the return values on the blocks. So integer encrypted len is going to be equal to that, and then decrypted len, and then we want to pass the encrypted length as the value into there. So yeah, just make sure that you update the parameters there. So then this should now be fixed. Uh-oh. This is no good. What is happening? Is there a memory error? No. This is weird. The encrypted length is going to be 32. Maybe I should debug and make sure that it actually returned 32. So break 27, run. So print encrypted length 16. That's not right. And then print decrypted length 0. Okay. So what is encrypt returning? Out length. Out length is number of blocks times the block length. Ah, I think I know why. Make sure that when you're doing number of blocks, that calculation, the n right shifted by 4 should be in parentheses, because I think that is, that's a, takes less precedence, so the addition will be performed first, yes. So make sure that n right shifted by 4 is in parentheses, and then make sure that is the same in decrypt as well. If that's, no, it's not in there. So yeah. So now, run. There we go. Looks good. But why is the cipher? Ah, yeah. Okay, so the cipher, because we have this extra block there, we're gonna get that cipher. So let me show you where this last block would be by looking at the number of padding characters. So debug break AES.c at line 387. If I run, if I go next, print number of padding, and we get 16, because once again we sent in complete block, 2 complete blocks, 30 length of 32. It gives us 16 an extra block. All right, so let me just continue. Quit. Let me change the text here so it's not a complete block. AES.c at line 387. Run. Next, print number of padding. And it's going to be not 16 characters. That's not what we want. It still gives us the right decrypted block, but did I not save it? Ah, yeah, because I didn't change the length. So this should be, instead of 32, 27. Okay. Alright, we get... That's not right. Oh wait, no, that is right. debug break for number of padding, and we get 5 because I deleted 5 characters. 27 plus 5 is 32 to get to a complete block, so that's the number of characters to get to a complete block. So yeah, that is the padding. Too many hiccups for something that's not as complicated, but yeah. So yeah, we got our plain text back. All good there. Okay. I'm just gonna implement counters or variables here, so this is less. Yeah. Okay. So yeah, that is padding using the PKCS5 method. Pretty cool stuff. But yeah, so padding is always good because you don't just want to. You need to consider just to make this cipher work. We need complete blocks, but just adding zeros may not be the best option, simply because we may want zeros otherwise. But if we always pad and we always know the last character will be the number of padded characters, then it just makes it a little simpler. I mean, you could also do where you do a bunch of zeros and then have the last byte equal to the number of padding bytes, but it doesn't make a difference. This just kind of simplifies it, so we either have the text or the length of or the number of padding bytes. There's no extra if statement. There's no third if statement there. It's just one or the other. All right, so yeah, that's padding. Now let's go and look at modes of AES. So I took this from an NIST document on block cipher modes. And we're going to be looking at 3 of them. The ECB, CBC, and CTR. We've already implemented one of them, ECB, which is just electronic code book. And the reason why is because it's simply you just take the plain text, encrypt it as a ciphertext, and then to decrypt, you just pass the ciphertext over to be decrypted. And that's all we're doing right now. We're not changing it in any way. We're simply taking, where is it? Yeah, we're taking the encrypted block, which is up here. Yep. We're just encrypting the block, writing it to the output, no modifications, and then we're taking that output, sending it to the decrypt function, and just decrypting it as is right there. So there's nothing changing. Or, yeah. Now this could be bad because if you have the same plain text and you're using the same key, which you might want to, like for example, if you had something on your hard drive, you would pretty much be using the user's password as the AES key. I guess padded, but still, you would be using it as the AES key. So what that would give is, if we had the same key and the same start of a file, you would be able to kind of see commonalities, and then you might be vulnerable to a frequency attack. I mean, not really, but that could be a possibility. But also, if a hacker deduced what the contents of one block was, and they saw the same encrypted block elsewhere, they would be able to deduce the contents of that other block if it was just ECB using the same key. However, there are different ways to deal with this. One of them is called CBC, which is the second one, which is called an acronym for cipher block chaining. So chaining, the reason why it's called chaining is because we're chaining modifications. So if you've looked into AES, you've probably heard of something called an IV, or an initialization vector, and all it pretty much is it's just a vector or a block of bytes. It's going to be a 16-bit or 16-byte block that we're going to XOR with the plain text and then the cipher when we're encrypting and decrypting. So the way it works is we take our plain text, which is in these blocks. Let me get a red over here. So not that red. That's too thick. So these are the plain text blocks. That's just the number of blocks. And once again, this will also work with padding. We take our initialization vector, which is just usually it's going to be a random string. So random 16-byte string. So the initialization vector, you're going to XOR it with the first block. This is the XOR operation here. That's XOR. So we're modifying the text using the initialization vector, which you might be wondering, well, what difference does this make from a key? Well, if you are the trick is you can never use the same key vector pair, because then you would have the same thing. But then we give the initialization vector, XOR it with the text, and that's always random. So even if two blocks were the same, they would not be the same when we pass them into the encryption function. Because, and the reason why, is because even if these two same blocks use the same initialization vector, we're going to be chaining that encrypted block to go to the next block as the IV. So whatever we encrypt here, the output of the encryption of the first block is passed in as the IV of the second block. So we essentially encrypt the XOR operation of the previous ciphertext with the next plain text, like that. So it just propagates along the chain, like so. And then for decryption, we're going to do pretty much the same thing. We take the initialization vector, and once we have decrypted something, we're going to XOR it with the decrypted block to get the plain text. And then for the second block, we will XOR the decrypted block with the previous ciphertext. And because once again, XOR is its own inverse, so we're just going to be XORing it with the same stuff. But notice here how we use the ciphertext both times as the XOR. Now, what could be a problem here? Well, first of all, if you use the same key IV pair, it doesn't really change anything. If you have the same first block, someone would be able to deduce what another block was if they found out what one of them was. So yeah, that's why the IV is usually going to be random. But another possible error here is that we could see some error propagation. So for example, if in the transmission here of say ciphertext 2 or ciphertext 1, we see that some of these bytes are flipped, so zeros become a 1 and a 1 becomes a 0. So we're something like along the lines of that. So all the bytes, or even just one byte, so let's say a 1 0 becomes a 1. It's only going to be one single byte that's fucked up in the ciphertext that we want to decrypt. However, this whole thing is going to be propagated. So along this line, we're going to propagate that error. And when we XOR it with the decrypted second block, we're going to be getting the incorrect results because there is that difference in the byte. So the XOR operation will not be the same. And then, so yeah, it will propagate across to the next block. So you could see how this would be a problem. It wouldn't be a big problem, but it definitely can. It will cause corruption. And yeah, so it just won't be good, and especially if you have like problems going, if you have a bunch of problems in like several different blocks, then yeah, you're going to see that error propagate much further, or there's going to be a lot of more error propagation. So yeah, that is CBC. Good stuff, but there is possibility for error propagation, which is not what we want. Now the third method we're going to look at, there are a few others. There's the cipher feedback at CFB. We're not looking at that today, because this is like stealing, and I don't want to look at that. That's just a lot of stuff. Pretty complicated. The one I found that looked best to me was called the CTR, or the counter mode. So essentially, what this mode does is we still start with an IV. So this first counter here, you can just think of as the IV. So this could be random, but you might not want it to be. But yeah, so we started with the IV. And what we're going to do is we're going to encrypt the IV, or the counter. And we take that encrypted block and then XOR it with the plaintext. I did forget to say something. With the IV, you might be wondering, well, how do we decrypt it? How do we know which IV to use for the decryption? You can simply just paste the IV at the beginning of the message. Like if we were to send this along a network, or if we were to put this in a file, we could simply just put the IV in the front, and it wouldn't matter because they would have to know the key to decrypt stuff. There's no way to use the IV to determine something, because we do the IV before the encryption and after the decryption. So it's the IV operations are all shuffled around in the AES algorithm. So by the time we pass in the IV, it'll be shuffled around once we then pass the XORed message through the algorithm. So that's why you can just simply pass this IV. But once again, it has to be random. But it wouldn't make a difference if a hacker knew the IV, because they can't do anything with this ciphertext. The IV has nothing to do with the ciphertext out here that you would see in a network, because it's only the only operations are up here before encryption and then down here after decryption. All right, now for the counter. Once again, we're going to start with an IV or a counter, whatever you want to call it, and we're going to encrypt the counter. So using AES, we're going to encrypt the counter, and we get an encrypted value. And then we're going to XOR that with the plain text and get a ciphertext. And this works. Yeah, this definitely works. The reason why this is considered more advantageous than CBC is because there's no chaining. You don't see any connection between blocks. There is a distinct division here between successive blocks. There's no lines passing through. So if there's an error in the transmission of one block, it'll only affect that block's decryption, but it won't affect any other block. So yeah, this is guaranteed to be safe because you need the key to encrypt the counter, and you need the key to decrypt the counter. So even if you knew the counter, so once again, this is going to be an IV, so we would pass it along with the message or store it with the file, but they wouldn't be able to decrypt anything. And then, so to reverse this, they would need to decrypt. They would need to decrypt this, and then, or would that work? No, yeah, it would. So they would need to like unXOR the counter, I think. Wait, no. But yeah, I don't think that would work. But point is, they wouldn't be able to do anything without having the key. So it's secure. So we take the counter, encrypt it, XOR it with the plain text, and then pass it out as a ciphertext. Like, yeah. So the reason why this won't work is because if they wanted to know the plain text from this, they would have to unXOR it with the cipher, or just XOR it again with the cipher, with the encrypted key. However, they don't know the key to encrypt the counter, so they wouldn't be able to find out what to XOR it with to get the plain text. But then for decryption, you are going to encrypt the same IV and then just XOR it with the ciphertext, because you know the key here. key is known here. And then you get the plain text. And then to go to the next block, you just simply go counter +1. Just like that. And once again, there's no chaining, so you can't do shit. One error propagation will, or one error in the transmission will only affect that one block. And another thing you should notice is that when we're incrementing by 1, you might be thinking, well, you're only changing 1 byte. How is that going to help anything? Wouldn't you be able to like kind of see change? But once again, AES, the neighbors are, when you encrypt neighbor texts, they become vastly different things. So like even if we encrypted the number 5 and the number 6, which I think are off by like 1 bit. So 101, or if we did 4 and 5, which are off by 1 bit, you encrypted them, you would get vastly different things. So once again, you'll get different things for the ciphertext. All right, so yeah, that's counter mode, and we're going to be implementing once again the ECB, CBC, and CTR today. All right, so let's go into AES.h, and we're going to add our macros to define these functions, or these different modes, or to kind of differentiate. So in AES.h, we'll have macros here. So hashtag define AES ECB as 0. Define AES CBC as 1, and define AES CTR as 2. All right, then we have our reference tables, and we can add a utility method to generate a random array. Because, once again, we're going to need a random array for the IV. So let's actually put this in cmathematics.h. So it's going to be void random character array, pass an unsigned character pointer array, and integer n. Now in cmathematics.c, let's paste the signature over, and then let's include time, because we're going to want to seed the, so include time.h, because we're going to need to seed the random generator. And then all we're going to do in random character array, let me just find it. Yep, we're going to see the random number generator using srand, and then pass in time at 0, which just gets the current time. Then we're going to say for integer I is equal to 0, I is less than n, I plus plus. The array at I is equal to random, bitwise, and with 0xff, so we're going to cap it. Cap at 255. So it's as simple as that. All right, now that's all we're going to be doing for cmathematics.h and .c. Now for AES.h and .c, we're going to need to be changing some method parameters, because once again, we're going to want to integrate an IV into here. So for AES encrypt, we're going to add 2 parameters after the key. We'll have an unsigned character mode and an unsigned character array IV of length 16. And then for AES encrypt block, after the subkeys, we will pass in the IV as an array of length 16. And then for decrypt, it's going to be the same thing. After the key, pass in an unsigned character mode and an unsigned character IV array of length 16. And then for the decrypt block, unsigned character IV of length 16. Now you might be wondering, well, why don't we pass the mode into encrypt and decrypt block? Well, if you look at all these diagrams, none of these are changing the actual AES algorithm. It's still going to be the same process of going through the rounds of adding the round key, shifting the rows, doing whatnot, whatever. It's just how you are going to be using that AES algorithm in the general context of a block cipher. This is why this document is not specific to AES. This is simply, I can go to it's the NIST recommendations for block cipher modes of operation. It doesn't care, it doesn't give two fucks about what block cipher mode you're using, or what block cipher you're using. You can use this for any block cipher, AES, DES, I forget the others, but yeah, it's as simple as this. No, not as simple as this, that's the wrong word. But yeah, so this is just in the general context of a block cipher. So that's why we're only passing it in as the mode and not, or only passing it into the general function and not each block. Because each block is where we actually perform the AES algorithm. But in decrypt and encrypt, that's where we are going to put the use or call the AES algorithm. Alright, then let's go ahead and copy and paste the new signatures into AES.c. So for decrypt, it's going to be paste in there. Decrypt block, only paste in the IV and not the mode. For encrypt, we want to paste in both. And then for encrypt block, only want the IV. Alright, now when we're going to start with doing two things. We're going to do the encrypt block and decrypt block, and we're going to change those. The reason why is because that's going to be the simplest thing to start with. So for encrypt block, when we're reading in the message to the state, we're going to pad the message, and then we're going to XOR it with the IV. This is what we're always going to do no matter what. So this will be affecting, or not really affecting, the AES algorithm, but we're going to want to do it here, just because this is when we read it into the state. So after we pad it, or after we determine the padding, we're going to say if IV, because we might not have an IV. We might pass a null specifically when we are using the ECB. There's no IB or no IV in here. So if there is an IV, then we will XOR it with the IV. So state at R at C, XOR equals IV at I. And then that's why we increment the counter afterwards. And then, on the other hand, for decrypt block, we're going to XOR it as we're outputting. So when we copy the bytes of the state into the output column by column. So we're going to say out at I, don't increment the counter yet. Out at I is equal to state at R at C, and then if IV, XOR with the IV. So out at I, XOR equals IV at I. And then afterwards increment the counter by 1, so I++. Just like that. Alright, so let's set up our main loops now to deal with this stuff. So let's go into, we'll start in encrypt and then we'll do decrypt. So in AES encrypt, let's go into our main loop and we calculate the length, keep that, but delete, or just comment out AES encrypt block for now. And then we're going to do a switch. So switch on the mode, what we'll do is we will have ECB by default. So we'll do case AES CBC break, case AES CTR break, and then default. Just like that. So we'll do a switch on the mode, and then we can just copy and paste this switch into decrypt as well. However, for decrypt, we're going to need to add just a counter, a variable here. Integer length is equal to block length, and just leave it like that for now. We're going to be changing this later on, but for now, just leave it like that. Okay, let's go into AES let's go into AES encrypt, and let's go into the switch. So we will start with the default ECB because we already know that, and all it is we are simply passing in the text and encrypting. So pass in the text and encrypt. So call AES encrypt block, and the parameters are going to be the exact same as before, except this time we're passing in the IV as null because we don't want to XOR it with anything. So the parameters are going to be the in text plus I left shifted by 4 in parentheses. The length is going to be length. Subkeys NR. The IV will be null. Then for the output, we're going to do a dereference of out plus I left shifted by 4. Just like that. Alright, and then we will, for decrypt ECB, it's pretty much going to be the same thing. It's going to be the same call that we had before, except this time we're passing in a null as the IV. So AES decrypt block. The in cipher will be in cipher plus I left shifted by 4. Subkeys NR, null for the IV, and then the output will be padded out. Because once again, we're still using padding plus I left shifted by 4. And one thing to note, even if it is padded, so in AES encrypt, even if we do pad the message, it's still going to get XORed with the IV, no matter what. It doesn't matter. All right. So now let's do CBC, because I think counter will be the hardest one to wrap, not the hardest one, but CBC is a good starting point, and then we'll do CTR. Alright, so for CBC, how did it work again? We have that the first IV is the IV that we pass into the function. So if I is 0, we can say if not I, then use passed in IV for the first block. So AES decrypt, sorry, I'm in the wrong reference function right now. I need to go to AES encrypt, yeah. So AES encrypt block, the text will be in text plus I left shifted by 4. The length is going to be, or the N will be the length. Subkeys, NR, the IV will be IV, and then the output will be a dereference of out plus I left shifted by 4. Otherwise, we're going to use the previous encrypted block as the IV. So it's going to be the same call, so you can just copy and paste the call, except for the IV, we're going to be passing in the previous output block. So a dereference of out plus then in parentheses, and another set of parentheses I-1. So do the I-1 first, and then left shift by 4. So essentially just getting the previous block. Get previously encrypted block. Alright, and then for decrypt, it's going to be extremely similar. For CBC, we're going to say, if not I. So if not I, then we're going to call AES decrypt block. The cipher will be in cipher plus I left shifted by 4. That's always going to be the same. Subkeys will be subkeys. NR for number of rounds. The IV will be the IV. And then for the output, it's going to be padded out plus I left shifted by 4. And once again, make sure that your left shifts here are always in parentheses because they take less precedence. And when we're doing pointer arithmetic, we just want to add the value as the cursor and not left shift anything by 4. Now, otherwise, we're going to call AES decrypt block again. Pass in cipher plus I left shifted by 4. Subkeys NR. The IV this time will be the previously encrypted block. So in cipher, we're still going to the cipher, plus I minus 1 in parentheses left shifted by 4. And then for the output, it's going to be padded out plus I left shifted by 4. But yeah, so we take the previously encrypted block, not the previously decrypted block, because then that would be just XORing it with the plain text, which would do nothing for us. We need to XOR it with the same thing that we XORed it with in the first place, which is the previous ciphertext. Now for the counter. All right, let's head into encrypt, AES encrypt. And we're actually going to start outside the loop. After we have created the keys, we're going to have two variables. We're going to have a counter. So we'll have an unsigned character pointer counter, which is equal to null, and an unsigned character pointer TMP, which is equal to null. The counter will just be the counter. That's what we're going to be incrementing, which will be okay. I don't want to encrypt. I don't want to increment the IV because we want to pass that IV along with the file or the message, so I don't want to touch that. The reason why we're going to need a temporary variable is because a note about CTR is that it may not be a block, so it may not have a complete block at the end, and that doesn't matter. We only need to XOR it with how many of our bytes are left over, and we'll still get the same result. So yeah, the remaining bits of the encrypted counter in the last block are just discarded. We don't really give a shit about them, which is another advantage of the CTR mode. However, to kind of do this, we're going to want to encrypt the counter every time and then pass it on to the output, or to the padded output. But then we don't want to XOR it with each byte of the counter because we don't have enough sufficient bytes from the plain text to XOR it with. So let's say in the last block we had 5 bytes of the plain text left. We're still going to get a 16-byte block for the encrypted counter, but we won't have 16 bytes to XOR it with. So we're going to only have 5 bytes to XOR it with. And then from there, we can... what was I going to say? But yeah, for that reason, we're going to need to have a temporary array to kind of pass it along to, so we don't have to reallocate memory. So what we're going to do is, if the mode is equal to AES CTR, then counter is equal to malloc block length times the size of an unsigned character, and then mem copy. So we want to copy over the initial vector. So the destination is counter, source is IV, and the size is going to be block length times the size of an unsigned character. And then for the temporary, it's going to be temp is equal to malloc block length times the size of an unsigned character. So once again, this temporary variable is always going to be a 16-byte string, and that's going to be the destination of our encrypted counters. But because we're not going to have that many bytes in the output, then we're just going to only XOR the necessary bits. Now, the reason why, or the way this difference is going to appear is, like I said, in how many bits we have allocated for the output. So instead of just allocating the out length, we're going to say if the mode is equal to AES CTR, then allocate for the length, which is not padded. So the dereference of out is equal to malloc n, which is the length of the input string, times the size of an unsigned character. And then else, we're just going to output the out, or allocate for the out length. Output is equal to malloc out length times the size of an unsigned character. CBC and ECB will say the same. Now for CTR, what we're first going to do is we're just going to follow the steps. So encrypt the counter and write to the complete temporary block. Then XOR with the plain text block, which may be incomplete. And then finally increment the counter by 1. So for encrypting the counter, we're going to call AES encrypt block on the counter. So the counter is going to be the input text. The number or the size of this block is going to be block length because it's a complete block, so we don't need to pad. Subkeys, number of rounds. The IV will just be null because we are not using an IV to XOR it with. And then the output will be the temporary block. So once again, we have a temporary block that is 16 bytes in length. Now the reason why we can't write to out is because if we have the CTR, we may not allocate for complete blocks at the end. So this last block would be trying to write to a 16-byte output, but it doesn't have that memory. So we need to first write it to a temporary and then XOR. So now we're going to say for integer j is equal to 0, j is less than length, j++. And then we're going to say in parentheses, the dereference of out at. Now for the index of the character, it's going to be in parentheses I left shifted by 4, close parentheses, plus j. So we're moving up to the block, to the current block, using I left shifted by 4, which is what you see over here, which is, just what we have already in the previous call to encrypt block. And then now we're adding j to get to the current character. So this is equal to temporary at j XORed with the corresponding character in the input text. So in text at, in parentheses, I left shifted by 4 plus j. And that's how we XOR it with the plain text block. And then for incrementing the counter, this is going to be a bit of stuff that we saw with the big integer, but we're going to increment assuming the lowest digit or the lowest magnitude digit is at the right side. So the last value or the last element in the array. So for integer j is equal to block length minus 1, and j is greater than or equal to 0, j minus minus, so count, so move from right to left, RTL, we're going to say if counter at j is equal to the complement of 0. So if max value, we can do this since we're using unsigned. So we'll have an overflow and carry with an increment by 1. So if we did add 1, we would just set this counter to 0. I'm not going to go into the details here, but this is essentially how you would do big. This is how we have done big integer or addition. And then here, otherwise we're going to increment it by the 1 because we have space. So increment by 1, simply say counter at j++, and then break. Alright, and then at the end we just need to change a few things. So delete the return statement, and we're going to say if mode is equal to AES CTR, we need to free the two variables. So free counter, free temporary, and then we're going to return n as the length of the cipher. And then otherwise return out length as before. Once again, n will be the length, so the output of CTR will be the same length as the input text, which is cool. Now for decryption, it's going to be largely the same thing, except we're just following the steps in a different way. So for decrypt, we need to start after we have allocated the subkey. Then we're going to allocate memory for CTR variables. So if mode is equal to AES CTR, then we're just going to allocate for the counter. So counter is equal to malloc block length times the size of an unsigned character, and then we want to copy the values over, or I need to actually set the variable. So unsigned character pointer counter is equal to null, and counter is equal to malloc that, and then memcopy destination is counter, source is going to be IV, and then we're going to copy over block length times the size of an unsigned character. Now we don't need a temporary here because we have a padded output which has complete blocks, which is all we need. And these complete, and we know that it has enough blocks because if we have an extra, this is why we changed up the value of n earlier, or this is why we use these counters earlier, because once again with CTR you may have an incomplete block for the decryption as a cipher, so we're going to need to have that extra value, but then we're just going to allocate that memory for a complete block there to the padded output because we're going to be removing that either way, and this just makes it a little simpler and more standard with everything else. So we still allocate the padded output. Now in the main loop, instead of having the length as block length, we're first going to check something. So set the length by default to a complete block, but if I is equal to number of blocks minus 1 and extra, there is an extra value, then we know that we have the incomplete block from CTR. So we're going to say the length is equal to extra, because that's just the number of bytes that we can XOR with. Alright, and then for AES CTR in the case, we're going to encrypt the counter. Once again, what's interesting about AES CTR is we never actually call the decryption algorithm. We're only encrypting the counter. So AES encrypt block, pass in the counter, block length, subkeys, NR, the IV is null, and then the output will be the padded output plus I left shifted by 4. Then we're going to XOR with the ciphertext block, may be incomplete. So that's why we have the length variable. So for integer j is equal to 0, j is less than length, j++. Then it's going to be the same stuff. Padded out at the index, I is less than, or I left shifted by 4 in parentheses plus j, XORed equals in cipher at the same index, I left shifted by 4 plus j. Here, once again, we don't need to use a temporary variable, so we can simply just XOR it directly with there. And then we want to increment the counter by 1. So I'm just going to copy the loop over that we had above, just because I don't want to write it again. But once again, this loop here, all it does is it just kind of accounts for a carry. And the only time we would have carry in when incrementing by 1 is if the byte is at 255. And that's only when we would, and that's the only time we would have a carry when incrementing by 1, because it would go to 256, which would wrap around to 0. All right. And then afterwards, the only thing this is going to affect now is just the number of padding values, because the number of padding characters is no longer the last character. It's going to be the leftover space in the block after the extra characters. So we're going to allocate number of padding as 0 by default. But if mode is equal to AES CTR, then the number of padding is just equal to block length minus extra. So padding is considered as number of characters, leftover characters in the incomplete block. And then we're going to free the counter afterwards. And then otherwise, we're going to set number of padding to what we had before, which is going to be the last character. So padded out at number of blocks times the block length minus 1. So get the last character there. And everything else is going to be the same. So yeah, this system here with the encrypting to the complete block just kind of integrates well, so we don't need to allocate any new blocks or do anything too specific. So we keep the variations confined to the loop, where we just do the switch and then through a bit of allocation stuff, but nothing major in the structure of our encrypt and decrypt functions is being changed based on the mode. All right, let's test this stuff out to see what we can do. So we'll have our key, and then we also needed an IV now. So unsigned character pointer IV is equal to, I'll just do ZYX WX TUV NOP IJKLM. Yeah, I think that's all right. Whatever. I was just counting backwards in the going backwards in the alphabet for the IV. So I'll now have. Let's have an array of 3 pointers, so 3 strings. And this is going to be just an array of 3 nulls. So I'm just going to do a few things here. I'm just going to go, so for int I is equal to 0, I is less than 3, I plus plus, and then we'll do the modes. And then I'll also have a name. So ECB, CBC, and then CTR, like so. And then we'll do integer encrypted length is equal to AES encrypt. The text length n, the key is the key, key length is AES 128. The mode will be I, since it just goes 0, 1, 2, right here. Then the output, or the IV will be the IV, and then the output will just be cipher plus. Is that right? I don't know if it is. Yes, it is. Cipher plus I. And then int decrypted length. I'm just creating an array of strings and just writing two of them. So is equal to AES encrypt txt or cipher at I n or encrypted length key AES 128 I is the mode, the IV is the IV, and then the output will be decrypted plus I. So the ith element in the array. Then we want to print out some stuff. So printf and %s. And then I'll kind of do the same stuff where we just print out the values. So print out the text key. Then we'll do cipher at I and decrypted at I. And then we'll free the values. So free cipher at I and free decrypted at I. And then at the end, we just need to free the text, the key, and then the IV. So if this code is correct, we should be getting 3 things that work properly. Run. Aha. Good stuff. So AES ECB. No, this isn't working. Fuck. So the plain text is there. The key is that. Oh, I know why. Because, wait, is that right? Is, let me try passing a null here and see if that works, but I don't think that is the problem. It might just be that we're getting the wrong encrypted length. Yeah, that's what it looks like. Because CTR works. We can see that right here. CTR works. It gives us the same length, and you see that the cipher is the same length as the cipher is the same length as the plain text, which is cool. Key is still 16. And then decrypt is correct. So it has to be a padding thing where I'm fucking up. It may be giving me an extra block where I don't want it. No, it wouldn't be. That wouldn't be an IV thing. So that's gonna be a padding thing. Oh, because I called. Oh, I'm an idiot. I called. I call AES encrypt and then encrypt again. But notice, guys, notice how even though I did that for AES CTR, it still gave us the same shit. Because AES CTR encryption is the same thing as AES CTR decryption. It's the same shit. Which is, I actually didn't know that. But that's kind of cool that we figured that out. So now let me run this. and we get this good shit. So let's compare them. So AES, ECB, and CBC, we see that they pad the ciphers to get to a complete block. Both of them pad there. CTR does not need a pad. We have the key, we have the IV, but then they all work, which is fucking awesome. And just in time for this album to be coming to a close. But yeah. So that is our wrap on the advanced encryption standard. I will be adding the key schedules for 192 and 256-bit keys, because I kind of figured that out a little bit ago, I think yesterday actually. But then I did CTR a bit after that. But yeah. So yeah, we have the key. That's cool stuff. I actually didn't know that AES CTR was its own inverse, which is fucking awesome. I'm liking CTR a lot more now. Yeah, I really like CTR now. But yeah, so that's all I got for you guys today. Hope you guys learned a few things. Yeah, we have 3 solid methods, compared them, contrasted them, wrote a few essays about why they were different, how they were similar. But yeah, that's all I have for you guys today. Hope you learned something. Once again, I'll be uploading the key schedules for 192 and 256 probably later tonight. And then I'm not sure what we'll be doing next in CMath. Maybe hash functions, because I kind of want to do some more encryption shit, because I want to do a nice... we've been doing a lot of this math stuff, and I guess we have been using it with OpenGL a little bit, but not like too much. Like, we haven't directly integrated this math library with the OpenGL stuff. I mean, we did at some point, but then we just figured out it was pointless to do that, because we were using GLM either way. But I want to do like an actual project with encryption here. Maybe like a password manager or something like that. But yeah, that's all I have for you guys today. Take care of yourselves. Be safe. Please don't die. That'd be kind of sad. And yeah, I will see you guys next time. Have a good night.